Hello everyone. Welcome back to Exploring Quantum Physics. I'm Charles Clark, and this lecture is going to discuss the theory and applications of angular momentum. Very important concept in quantum physics, and one that in some sense defines a larger framework within which we look at many problems. You might say everything revolves around angular momentum. Joke, get it? But it is, in fact, a very important framework, and I'll just draw your attention to a random example from the additional materials sections under the title Atomic Clocks and Quantum Computers. This is a figure from a paper written by David Wineland, who won the Nobel Prize in Physics last year. And it's a visionary paper that describes the relationship between atomic clocks and quantum computers, and actually provided a roadmap for the development of the first practical quantum computing device, as I see it, which was this an optical clock based on the aluminum ion. Now, what you see here is a schematic of two atomic energy level structures, and they're given, a number of these very precise labels. It's not like 5 halves. It's not like 2.6. It's exactly 5 halves. So there are these various quantum numbers, and I don't expect you to necessarily recognize these right now, but these all are developed on the basis of an understanding of the conservation of angular momentum in quantum systems and its quantization. And this is extremely important. It underpins everything: atomic clocks, the operation of magnets at a fundamental level, and so on. So in this lecture, we're going to go through some of the fundamental techniques that are required to develop and use the theory of angular momentum in quantum mechanics. So in particular, we're going to derive a number of foundational properties of the angular momentum operators. And I'm going to introduce something that is pretty standard set of procedures for tensor calculus. They're very useful in developing a practical understanding of how you deal with angular momentum algebra. And so some of you may be familiar with these. In that case, the first few parts of this lecture might be sort of a review or tutorial. We're using an approach that was first developed by Albert Einstein, and it seems at first like sort of just a notational innovation, but it has a lot of important practical consequences, and is useful in many areas of physics. Now, for the sake of simplicity, we're going to use vector notation, but all the symbols denote operators. So, in other words, the angular momentum in classical mechanics is this object, and we saw its significance in the context of the classical theory of the hydrogen atom earlier. So now we're treating it as, well, let's say, a vector-valued operator. So it has 3 components, right? Lx is equal to xpy minus y. Lz is equal to xpy minus ypz. Ypx. Sorry. And then there's an Ly and an Lx as well. So there's but these are now to be interpreted in terms of the quantum mechanical operators. So I'm going to switch notation because, as it turns out, it's much easier to do calculations when you don't have different symbols for coordinates, but you just have a different subscript. So hereafter, we're going to use a convention x1, x2, and x3 for the coordinates, and then for the unit vectors, e1, e2, and e3. But, occasionally we may lapse and switch back. Okay, so now the first thing that you should take a note of, this is going to become important in the derivations, is the use of the Einstein summation convention for repeated indices. This was something that's actually discovered by first pointed out by Einstein. And he said, well, he noticed there are lots of expressions of this type. Here's the scalar product of 2 vectors, A and B, which in our new notation we would write these as sum of AI VI. And what Einstein noted is that you can just, in cases like that, you can just cross out the summation sign. And so whenever you encounter an expression of this type, you implicitly sum over a repeated index. That saves the presence of having large numbers of summation signs. Now, you do have to be careful when you do this, but that's why we're going to engage in some practice. Another tool that's the third of these tools, really useful, is the Levi-Civita symbol. So this has a 3 subscripts, and it takes the values +1, -1, or 0 according to whether, in the first instance, if the symbols I, J, K are a cyclic or even permutation of the symbols 1, 2, 3. So you can see, okay, 1, 2, 3. If you shift that back with a revolving displacement of the index, it goes to 2, 3, 1. Shift it back again, it's 3, 1, 2. Then again, it returns to itself. The odd permutations are those which involve just a transposition of 2 elements. So 1, 2, 3. If you switch 1 and 2, you get 2, 1, 3, and so on. So the Levi-Civita symbol is -1 in cases like that, and then it's 0 otherwise, meaning when, for example, 2 or more of the indices are the same. So in other words, it vanishes unless every one of these, every value of the index is present. So now the in-video quiz will ask you to construct the vector cross product using some of the tools that we've just described. So that example just showed you how you can use the Einstein convention, Levi-Civita symbols, and the index system to conveniently do standard procedures of vector algebra, which you find useful in electromagnetism and mechanics. And we'll make use of such examples in further discussion here. Now, finally, there's a very important contraction identity of this form. So all I can say is look at this carefully. Here's the Einstein summation convention, and you see there's we call it a contraction identity because there's a duplication of 2 of the indices. When that happens, it turns out that you can reduce this product of the Levi-Civita symbols to sum of products of delta functions, Kronecker delta, which has the following definition. I think you're all familiar with that. Delta ij is equal to 1 if I is equal to j, and 0 otherwise. And I think it would be it's probably a good idea for you to pause and just look at this and run a few examples to convince yourself that it's true. So just to put everything together with one example, let's take something from classical vector calculus. A cross the quantity B cross C, something that arises very often in applications, and we'll use. So we use the summation convention and the Levi-Civita. and then so here we have a second. Here we see this pair of Levi-Civita symbols come in the full expansion. And basically, what we're doing here, we're getting down to sort of the most fundamental reduction of this quantity in terms of its components. So that's this, and now we see that we can apply the contraction identity thusly, and we end up. I think you want a good idea for you to look at this and follow it through offline, that we get the famous back cab rule, which is often used for resolving vector products. Okay, this is very much a methodological part of the lecture, so hope you'll review what you've learned, and then we're going to, in the next few parts of the lecture, start applying this to develop important information about angular momentum. Hope to see you again.